We defined uniform circular motion the other day as circular motion, which I think is pretty self-explanatory, right? Object moving in a circle. But specifically, the term uniform means moving at a constant speed as it goes around in a circle. Now, there is non-uniform circular motion as well. Absolutely, there's situations where objects move in a circle and either speed up or slow down. But that's not what we're going to be talking about. In this unit, we're going to talk about objects moving in a circle going at a constant speed, uniform circular motion. We defined two new terms the other day, two brand new terms. One was frequency. Anybody remember what we defined that as? The frequency is the number of cycles per unit time. And because of that definition, we could write the frequency in the form of an equation that does not appear on your data sheet. F is equal to number of cycles over the time. So I'm going to circle that in blue, but remember that one's not on your data sheet. It comes down to either remembering the equation or remembering the definition and figuring out one from the other. Now, the period is not the number of cycles per unit time, but rather it's the time per cycle. How much time does it take, in this case, to go around a circle one time? The time per cycle. What's the symbol for period, do you remember? The symbol, yeah. Good, it's capital T. Not just any T, but it's a capital T. Just lowercase t is just time in general, any amount of time. Time interval, whatever. Big T is specifically the amount of time for one complete cycle. If it's time per cycle, then we're going to divide the time over the number of cycles, which of course is exactly opposite to what frequency is. Also circled in blue, meaning that it does not appear on our data sheet. Do you guys remember the unit for frequency? Not the symbol, that's F, right? The unit is hertz, good. And does anybody remember the unit for period? The standard unit, that is. Sorry? No? Revolutions per minute would be frequency as well, although not the standard unit. Hertz or revolutions per second would be the standard unit. What is it for period? Seconds, good. Now, how does frequency and period relate to each other? We're going to put this one in blue because in green, because this one is on your data sheet. If frequency is cycles per time, period is time per cycle, then the period is equal to 1 over the frequency. Seconds is equal to 1 over seconds. And of course, speed. Speed is a constant speed because that's how we define uniform circular motion. Motion in a circle with a constant speed. What's the distance around a circle one time? What's it called? Its circumference. It's 2 pi r, the circumference. Not pi r squared, that's area, right? 2 pi r is the circumference. And what's the time around the circle one time? We just defined that a minute ago, right? It's the period. So we know that v is equal to 2 pi r over t. That does appear on your data sheet as well. So everything in the check mark beside it appears on your data sheet. Everything with an X does not appear on our data sheet. We did some questions the other day on this stuff, page 250, page 251. Any issues with either of those sets? No, relatively straightforward, I think. Relatively. Some of them are harder than others, but. All right. Well, today I want to move forward a little bit and talk about one of the main thrusts of this unit, and that is these two new terms, centripetal acceleration and centripetal force. We talked about this briefly the other day, but we didn't write anything down on it. We said as an object moves around in a circle, it moves at a constant speed, but at the same time, it accelerates. How is that possible? How is it possible that these keys swinging around my head are moving at a constant or uniform speed, but yet accelerating? How do we define acceleration? Ben? Yes. Acceleration is defined as the rate of change of velocity. Not the rate of change of speed, the rate of change of velocity. And velocity is it's a vector. So direction matters. So when we talk about acceleration, we're not necessarily talking about a speed change, although that's usually what it is, right? A speed change. But we could also be talking about a direction change. That's what we've got with centripetal acceleration. It's object moving in a circle. There's an acceleration, not because the speed is changing, but because the direction it's constantly changing. That centripetal acceleration, is that acceleration that's causing these keys as I swing them around my head to go in the circle. That acceleration is directed toward the center of the circle. That's what we call it centripetal. Centripetal means center seeking. Now, it's a little bit hard to understand how we can have an acceleration directed toward the center of a circle. Like, it's not even ever moving toward the center of the circle. It's moving in a circle, but yet the acceleration is always inward toward the center of the circle. You'll see why in a moment that it is directed inward toward the center of a circle. Let me define another term first, though, the centripetal force. When there's an acceleration, there must be a force. The force is the force that's acting on those keys or whatever it is that's moving in a circle that is directed toward the center of the circle. A little bit easier to see why that's directed toward the center of the circle. As I swing my keys around my head again on the end of this lanyard, what is it that pulls them toward the center of the circle? Well, the centripetal force, right? But something always causes the centripetal force. It's never a force that acts on its own. It's always caused by something. In the case of the Earth going around the sun, the centripetal force is caused by gravity. In the case of a car going around a turn, the centripetal force is caused by friction. In the case of the keys going around my head, the centripetal force is caused by tension in the lanyard, right? Which ultimately is caused by what? What's pulling on the lanyard to pull the keys? My hand, my wrist, right? Where's my hand or my wrist? In the middle. So my hand is pulling on the keys toward the center of the circle. The centripetal force is toward the center of the circle. And if the force is toward the center, well, then the acceleration must be toward the center as well, because F is equal to m times a. Let me give you a new equation, an equation that does appear on my data sheet for centripetal acceleration. We're going to say that A, with two vertical lines on either side of it, what does that mean? We've seen this before, right, with force of friction. Absolute value, good. That means that when we calculate this force, this acceleration, there is a direction associated with it, but we're not going to get that direction from the equation. The equation is going to give me only the magnitude of the acceleration. You know what? That's okay. The direction is easy to find. We know that the direction is always which way? Toward the center. We don't need an equation to tell me which direction it is. We know the direction. It's toward the center of the circle. So this equation doesn't give me the direction. That's okay. It does give me the magnitude. V squared over r. What does V stand for? Good. It's the speed, not the velocity. It's the speed of the object. And sometimes you may be given the speed. Sometimes you may need to find the speed by using V is equal to 2 pi r over t. What does r stand for? The radius of the circle. And the units for that would be meters. What do you think? A centripetal acceleration, of course, AC centripetal acceleration. What do you think the units would be for that? Meters per second squared. How does that come from this equation over here? Well, if you go meters per second and then square it, V squared over R in meters, because meters squared over second squared over meters, this cancels, and we're left with meters per second squared. So the centripetal acceleration, always directed toward the center of the circle, given in the units, and these meters per second squared, just like regular acceleration is. The one difference here is that the equation won't give you the direction like it does in our old F is equal to m times a equation. Here, we get the direction just because we know it's toward the center of the circle. Next one, centripetal force. Well, we know that F is equal to m times a. But what's a equal to? V squared over r. So we're going to say here that the centripetal force is equal to m times v squared over r. Once again, that does appear on our data sheet. V is speed, meters per second. R is radius in meters. F is centripetal force. M is mass in kilograms. Centripetal acceleration, centripetal force, both directed toward the center of the circle. Remember, I mentioned this briefly a second ago here. The centripetal force is that general term for the net force toward the center of the circle. It's always caused by something. It's always caused by something. Like when the Earth goes around the sun, you've got gravity holding it in place. Gravity is a fundamental force. It's not caused by any other force. It is what it is. But centripetal force, that we say is that general term for the force that keeps an object like the Earth going around the sun, is always caused by something like gravity, or like the tension in the rope, or like an electric force. Always something that causes that FC. Now, we've shown you which way the acceleration points, which way the force points. But what about the velocity? The velocity, which way does it point? Well, if we look at an object going in a circle, let's say counterclockwise like this, the velocity is always directed at a tangent to the circle. What does that mean? We did tangent lines back in Unit 1 when we were looking at the instantaneous velocity on a position-time graph, right? A tangent line is a line that kind of skips along a surface. So at this point, the velocity would be this way. At this point, the velocity would be this way, this way, this way, and so on. The velocity is at a tangent to the circle. The acceleration is toward the center of the circle, and the force is also toward the center of the circle. Does that make sense? If I swing these keys around my head, they accelerate toward the center. The force is toward the center. But if I was to suddenly remove that centripetal force by letting go or cutting this rope, what would happen? These keys would fly off and hit somebody, right? They would fly off in a straight line at a tangent to the circle. I think when we were talking about Newton's first law, I told you the story of how when I got my job as a teenager driving the delivery van, and I was going around that turnoff off of the highway, and there was a little bit of snow and ice on the road, and I was going around, here's the off-ramp, I was going around like this, going in a circle, right? There was a centripetal force provided by friction that caused me to go in that circle, right? That centripetal force pointing toward the center. But as soon as that ice disappeared, as soon as that centripetal force disappeared, where did I go? Off in a straight line. It's Newton's first law, right? If we remove the net force, the centripetal force, the friction that causes it, it's always going to go off in a straight line at a tangent to the circle. Let's look at an example, okay? A DVD disc. Man, we don't even use DVDs anymore. This is so like 2010. A DVD. Who uses DVDs anymore? Yeah, they don't even, they still make them and sell them for $5 at Walmart, right? DVD, same as a Blu-ray, has a diameter of 12 centimeters and a rotational period of 0.100 seconds. We want to find the acceleration at the outer edge of this disc. So we're going to say the diameter is 12.0 centimeters. We want to convert that to what? We don't want diameter. We want the radius, right? So the radius is going to be half of that, 6 centimeters, or I might as well convert that to meters right now, 0.600 meters. We have a rotational period of 0.100 seconds. What variable is that? Big T, right? Not just any T, it's big T. And we want to find the centripetal acceleration. Centripetal acceleration is v squared over r. We don't know what v is, so we've got to find it. How do you find v? How do you find v? Somebody said it, 2 pi r over t. Good. 2 times pi times 0.0600 divided by the period of 0.100 seconds. Let's figure that out. 2 times pi times 0.06 divided by 0.1 gives me a period of 3.7699. So this DVD, the outer edge of it, that is, would spin around at 3.7699 meters per second. We sub that into here. Want the unrounded number because it's not a final answer yet. Divided by r is 0.0600 meters. Let's square this number, and then let's divide that by 0.06. And we end up getting a value of 236.8, or we're going to round that to 3 digits. 236.8. Well, what would that be in 3 digits? Look, here's my 3 digits. Here's the 4th digit. Look at the one right after the 3. Okay, it's an 8, so it rounds up. That means that 236.8 becomes 237 meters per second squared. Or you could say 2.37 times 10 to the 2 meters per second squared. It's a pretty big acceleration. If you had a speck of dust on the outer edge of this DVD, it would experience about 24 Gs. What's a G? Well, 1 G is gravity. If you experience, as you will on the Mindbender roller coaster on our field trip coming up in just under a month, actually 4 weeks from today, then you will experience about 4.5 Gs at the bottom of the first hill. In other words, if you are truly 70 kilograms, you will feel upwards of about 300 or 350 kilograms at the bottom of that first hill. Now, a speck of dust or a bug on the edge of this DVD experiences 237 meters per second squared. That means that a bug or a speck of dust would experience about 24 Gs, about 24 times actual gravity. So if you were on this, you would feel 24 times heavier than you really are. 24 Gs. Yep. Yeah, well, that's a good question. The question is, did you pass out at about 6? Well, there's no way you'd ever sustain 24 Gs. Well, I shouldn't say that. For any kind of sustained period of time. When you play football, you sustain 24 Gs all the time. But it's a very, very, very short period of time. Now, if you were accelerating for a few seconds at 24 Gs, you would never stay conscious. The blood would rush from your head to your feet. And as the blood rushes from your head, the oxygen would disappear from your brain. And then what happens when the oxygen disappears from your brain? Eventually, but you pass out, right? It's called G-lock. Okay, fighter pilots, sometimes that's one of the major crashes of fighter plane crashes actually is G-lock. Pilots are turning really, really tight turns. They experience such a huge centripetal force that the blood can't stay in their brain, and they pass out, and the plane crashes because the pilot has passed out. Everybody can sustain a slightly different amount, but you mentioned 6 Gs. Depends on the person, but that's probably about right. Some people can sustain a little bit more than that for a few seconds. Some people would pass out before that. You're going to experience there's a double loop on the Mindbender at West Ed, like 2 loops in a row. And you're in those 2 loops for a few seconds, like upwards of about 4 seconds. You only experience about 3.5 to 4 Gs on those loops, but there's a good chance that you will begin to pass out. You won't pass out completely, but lots of you will experience this. You'll be going around there, you'll be looking forward, you're enjoying yourself, and all of a sudden your peripheral vision starts disappearing. So your vision starts getting narrower and narrower. Your eyes are wide open, but it gets blacker and blacker and blacker until you can't see. Your eyes are wide open, but everything is pitch black. You're getting close to passing out at that point. Now, it doesn't mean you have passed out, and in all likelihood, you won't pass out because you're not in those loops for long enough. But it's the start. It's not unhealthy. It's not damaging. But if you were to sustain that for minutes as opposed to 3 or 4 seconds, then it would be, right? Then it would start causing, some more long-term issues for you. Yeah?
So is that when I make a tackle in football, I never actually remember doing it?
All right, take a look at those 3 questions, please, on page 255. Centripetal acceleration. Oh, by the way, hey, what were we asked for, the centripetal acceleration? Did I answer that question? Acceleration is a vector. It needs direction. We didn't identify the direction, did we? Josh, which way is the direction? We know this. The equation is not going to tell me, but we know this. It's toward the center. Now, if it had asked me for the magnitude of the acceleration, 237 would have been fine. If it asks me for the acceleration, I want both magnitude and direction, 237 toward the center of the circle. All right, now let's take a look at those 3 questions, please, on page 255. Centripetal acceleration, including direction, speed, 2 pi r over t, and perhaps even t is equal to 1 over the frequency. See what you can do on those now. We're going to take a look at question number 1 and question number 3 here. Number 1 says you throw a frisbee to your friend. The frisbee has a diameter of 28 centimeters. There's a couple things we want to draw attention to there. The fact that we have centimeters, we want to convert that to meters, and the fact that we have a diameter, we want to convert that to a radius. So we're going to draw attention to both of those things. We want to find the acceleration, the centripetal acceleration at the outer edge. So we're going to say, for this question, A is equal to v squared over r. That's centripetal acceleration. We don't know what v is, so let's find it. V is equal to 2 pi r over t. 2 times pi times 0.14 divided by the period of 0.110. I think when we do that, we get 7.99. Was that right? What's the unrounded number there? 7.99. What was it, sorry? 67813. Thank you. Now we're going to square that. 7.9967813. Okay, squared divided by, be careful here because I know that a couple people divided that by 0.11, not by 0.14. We're dividing it by the radius, not by the period. So 0.14. When I do that, I should get 4.57 times 10 to the 2, or we could just say 457 meters per second squared. How many G's would that be? It's about 46, right? Divide by 9.81, and you're getting about 46 G's. So this would be way more than you would ever want to experience for any kind of sustained period of time. As you said, with the 24 G's, it would not end well for you if you sustained that for any kind of length of time. Yeah.
Is there any amount of G's that would be deadly after
Yes, after a short amount of time. Absolutely. I mean, people are killed in car accidents all the time. People are sometimes killed by a punch. That not often, but sometimes, right? And the reason for that is because they experience too many G's at one moment in a certain vulnerable place of their body. Yeah. 2, helicopter blade, number 3, I should say. A helicopter blade has a diameter of 14 meters, which, again, we want to draw attention to that because we want to convert that to radius. Here's the centripetal acceleration. What's the period of the helicopter blade? Well, we know this involves centripetal acceleration, so let's do our equation here. A is equal to v squared over r. Listen, we know what r is, and we know what a is, so let's solve for v here. It's not what we're looking for, but it's something, right? We've talked about this all year long. If you can't get what you're looking for, what should you do? Get something. Get something. Let's get v. A times r is equal to v squared. The r goes up by multiplying, and then v squared becomes equal to, v becomes equal to the square root of a times r. Does that make sense? If the r goes up by multiplying, then you got to square root it. So v becomes equal to the square root of a 2527 times r, which is, what's r? 7, right? 7. So v, let's figure that out now here. Let's say it's the square root of bracket 2527 times 7, 133. Is that what you guys got? Okay, there's the speed. Well, once we have the speed, what are we going to do? Now we find the period. How are we going to do that?
Use v equals 2 pi r over t.
Right. V is equal to 2 pi r over t. We're going to rearrange that to solve for t. It's 2 pi r over v. 2 times pi times 7.0 divided by 133. And when we do that, we should get 0.331 meters. 0.331 seconds, not meters per second. Next question here. It says, determine the magnitude of the centripetal force exerted by the rim of a dragster's wheel on a 45-kilogram tire. Here's the radius, here's the speed. This is pretty straightforward. Once find the centripetal force, we're going to say F is equal to mv squared over r. M is, by the way, sometimes I write centripetal force like this, and sometimes I write it like this. Is there a difference? No, mv squared all over r is the same as saying m times v squared over r. So it doesn't matter which way it's written, it doesn't matter which way you do it, okay, it gives you the same answer. M is 45.0 kilograms, and v is 30 meters per second. Let's divide that by r, which is 0.480. Let's figure out what that is now. On our calculator, we're going to say 45 times 30. Don't forget to square that. And then divide that by 0.480. That gives us a centripetal force of 8.44. Look, 84375 newtons. Or we want to round that to 3 digits, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. Here's my 3 digits. Here's my fourth. My fourth digit is 5 or greater, so we got to round that up. Instead of being 843, it would be 844. Now, we're going to have to actually put that into scientific notation because like 844 is not our answer, right? 8.44 times 10 to the 4. 1, 2, 3, 4. 8.44 times 10 to the 4 newtons. Now, technically, again, actually, no, this one is correct. Okay, why do I not need to put the direction in here? Because it asks for the magnitude. Good. It is directed toward the center of the circle, but clearly they're not looking for that direction in this question. All right, if you're good with that, let's take a look at these 2 questions, please, on page 256.